let's look at two examples on computations involved in error analysis. It's a fairly simple proposition. There are two cases that I'm going to explore in light of error analysis. The first one is we want to calculate the percentage error in determination of time period of a pendulum. You know, time period of a pendulum is given by 2 pi root L by G, where L and G are measured with plus minus 1% and plus minus 2% errors, right? I want to calculate the percentage error in the time period. Hey, fractional error in the time period is going to be given by half of, realize this is L to power half and G power half. So plus minus half delta L by L. See, this constant will not feature anywhere because there is no error in as far as 2 pi is concerned. So if I say delta 2 pi, that's obviously going to be 0. So delta L by L plus half of delta G by G. Delta L by L can be replaced by the fractional error in L, which is 1%, and delta G by G, fractional error in G, which is 2%. So that makes it 3 by 2, that makes it 1.5%. So fractional error in time period then produced is going to be plus minus 1.5%. This was one situation. Let me look at another situation, which is like the mass and density of a solid sphere are measured as 12.4 plus minus 0.1 kgs and density measured as 4.6 plus minus 0.2 kilograms per cubic meter. We want to calculate the volume of the sphere with the required error limits. Volume, of course, you know, is mass by density, right? So the mean volume can be looked upon as, well, mass, which is 12.4, divided by density, which is 4.6, which turns out to be roughly 2.7 cubic meters. Right? Now, the fractional error in volume is what we want to calculate. Using this result, the fractional error in volume would be plus minus fractional error in mass plus fractional error in density. Fractional error in mass plus fractional error in density. Now, what is the fractional error in mass? Fractional error in mass, as you can see, is 0.1 divided by 12.4. Fractional error in density is 0.2 divided by 4.6. And if I multiply it by volume, which is 2.7 cubic meters, I get delta V, which is the error in volume, which is plus minus 0.14. And therefore, the volume along with its limits would be V plus minus delta V. V is 2.7 plus minus 0.14. 0.14 is what we have computed. So the fractional, that's the representation of volume along with its errors, right? So, you know, these are simple problems, and I must tell you that almost in every exam you're going to encounter a problem that involves error analysis, measurements, and so on and so forth. So these are sitters, and to get used to all of this will make sense. It'll surely earn you marks, and also, you know, from the point of view of knowing the subject, it's important. So this much in terms of error analysis. Thanks a lot. Bye-bye.